the silent catastrophe brewing beneath your hood claims more engines than any other mechanical failure. Statistical analysis reveals that thermal damage accounts for more than half of all catastrophic engine failures. Yet most drivers remain blissfully unaware of the intricate ballet of components working tirelessly to prevent their engine from self. Every combustion cycle generates temperatures exceeding 2000 degrees, hot enough to melt aluminum pistons and warp steel components within seconds without proper heat management. Your engine cooling system represents one of the most underappreciated yet critical networks in your vehicle. This complex arrangement of pumps, passages, fluids, and heat exchangers maintains the delicate temperature balance that allows controlled explosions to propel you forward without reducing your engine to molten metal. Understanding and maintaining this system requires more than occasional glances at the temperature gauge when warning lights illuminate. The foundation of thermal management begins with the fluid coursing through your engine block and radiator. This engineered solution does far more than simply carry heat away from combustion chambers. Modern coolant formulations contain carefully balanced chemical packages that prevent corrosion, lubricate moving parts, raise boiling points, lower freezing temperatures, and maintain stable pH levels throughout years of service. Each of these functions proves essential for long-term reliability. As coolant ages, its protective additives become depleted through chemical reactions and thermal cycling. The fluid that once prevented rust formation gradually becomes acidic, actively attacking the very components it was designed to protect. Aluminum cylinder heads suffer pitting, iron blocks develop scale deposits, and rubber seals deteriorate when exposed to degraded coolant. These problems develop invisibly within closed systems, progressing from minor inefficiencies to major failures without warning. The timeline for coolant replacement varies depending on formulation and driving conditions, but waiting for problems to manifest guarantees expensive repairs. Modern extended life formulations may last 50,000 miles or more, while conventional coolants require replacement every 30,000 miles. The relatively modest cost of periodic coolant changes pales compared to replacing corroded radiators, failed water pumps, or damaged engine blocks resulting from neglected maintenance. Selecting appropriate coolant proves more complex than choosing the least expensive option available. Automotive manufacturers specify particular coolant chemistries based on the metals, seals, and gaskets used in their engines. Organic acid technology formulations protect different materials than inorganic acid technology or hybrid organic acid technology. Using incompatible formulations can trigger chemical reactions that create gel-like substances, clogging narrow passages and destroying pump seals. The consequences of coolant incompatibility extend beyond simple contamination. Different formulations establish different electrical potentials within cooling systems, potentially accelerating galvanic corrosion between dissimilar metals. Aluminum components suffer particularly severe damage when incorrect coolants create conditions for electrolytic degradation. Following manufacturer specifications ensures chemical compatibility with all system components. External cleanliness of heat exchange surfaces dramatically impacts cooling efficiency. Your radiator functions as a heat exchanger, transferring thermal energy from coolant to ambient air. This process requires maximum surface area exposure and unobstructed airflow through closely spaced cooling fins. Road debris, insects, leaves, and atmospheric contamination gradually accumulate on these surfaces, creating an insulating barrier that prevents effective heat dissipation. The forward-mounted air conditioning condenser compounds this problem by collecting debris before air reaches the radiator. Both components require periodic cleaning to maintain optimal performance. Gentle removal of surface contamination using soft brushes or compressed air prevents fin damage while restoring cooling capacity. High-pressure water should be avoided as it can bend delicate aluminum fins, permanently reducing heat transfer efficiency. Rubber hoses connecting cooling system components endure extreme conditions throughout their service life. These flexible conduits experience constant pressure fluctuations, temperature extremes ranging from sub-zero to near boiling, and exposure to petroleum products and road chemicals. The rubber compounds gradually lose plasticity, developing microscopic cracks that eventually progress to catastrophic failure. Visual inspection reveals only surface deterioration, while internal degradation often proceeds undetected. Hoses that appear serviceable externally may have deteriorated internally, with rubber particles breaking free to contaminate coolant and clog radiator passages. Proactive replacement based on age and mileage prevents roadside failures and secondary damage from coolant loss. The minimal cost of quality hoses represents cheap insurance against engine damage. The humble radiator cap performs a critical function that belies its simple appearance. This spring-loaded valve maintains system pressure at precisely calibrated levels, typically between 13 and 18 pounds per square inch. This pressurization raises the coolant boiling point by approximately 3 degrees for each pound of pressure, allowing the system to operate at temperatures that would cause unpressurized coolant to vaporize. A failing radiator cap cannot maintain proper system pressure, leading to coolant loss through evaporation and inadequate heat transfer. The rubber seals deteriorate with age and heat exposure, while the spring mechanism weakens over time. Regular inspection and periodic replacement ensure proper system pressurization and prevent coolant loss that could lead to overheating. Recognition of overheating symptoms and appropriate response can mean the difference between minor inconvenience and catastrophic engine damage. Rising temperature gauge readings demand immediate attention, not hopeful continuation toward your destination. Every moment an engine operates above normal temperature causes cumulative damage to gaskets, seals, and metal components that may not manifest immediately but will eventually result in failure. Proper response to overheating involves safely stopping the vehicle, allowing the engine to cool naturally, and investigating the cause before attempting to continue. Opening the hood accelerates cooling while avoiding the dangerous mistake of removing the radiator cap from a hot system. Pressurized coolant can violently erupt, causing severe burns. Patience during the cooling period prevents injury and allows proper diagnosis of the underlying problem. Water quality significantly impacts cooling system longevity, yet many people unknowingly introduce contaminants when topping off coolant levels. Tap water contains dissolved minerals that precipitate when heated, forming scale deposits on internal surfaces. These mineral deposits act as insulation, preventing efficient heat transfer and creating hotspots that accelerate component wear. Distilled water contains no dissolved minerals, making it the only appropriate choice for cooling system use. The minimal cost difference between distilled and tap water becomes insignificant when compared to the expense of removing scale deposits or replacing damaged components. This simple choice during routine maintenance prevents long-term problems that compromise cooling efficiency. Proper coolant level maintenance requires understanding thermal expansion principles. Cold coolant occupies less volume than hot coolant, necessitating an expansion reservoir to accommodate volume changes. Overfilling this reservoir prevents proper expansion, potentially causing system overpressurization and coolant loss through overflow valves. Conversely, insufficient coolant allows air pockets that create hotspots and accelerate pump cavitation. The correct fill level varies with temperature, requiring careful attention to hot and cold markings on reservoir tanks. Persistent coolant loss indicates system leaks requiring prompt attention rather than continued topping off. Small leaks inevitably progress to major failures, making early detection and repair essential for preventing roadside breakdowns. The water pump serves as the heart of your cooling system, circulating coolant through the engine block, cylinder heads, heater core, and radiator. This mechanical pump typically operates via belt drive from the crankshaft, though some modern designs use electric motors for improved efficiency. Bearing wear, seal, deterioration, and impeller erosion gradually reduce pumping efficiency over years of service. Early warning signs of pump failure include coolant seepage from weep holes, bearing noise during operation, and overheating at idle when airflow through the radiator decreases. Catastrophic pump failure leaves engines without coolant circulation, causing rapid temperature rise and potential severe damage within minutes. Scheduled replacement during timing belt service or at manufacturer-recommended intervals prevents unexpected failures. Belt condition directly impacts water pump operation in mechanically driven systems. Worn or improperly tensioned belts slip under load, reducing pump speed and coolant circulation. Modern serpentine belts may appear adequate while actually providing insufficient grip, particularly when contaminated with oil or coolant from nearby leaks. Regular inspection and timely replacement ensure proper pump operation. The cooling system thermostat regulates coolant flow based on temperature, maintaining optimal operating temperature for efficiency and emissions control. This temperature-sensitive valve remains closed during cold starts, allowing rapid warm-up, then opens to permit coolant circulation once operating temperature is reached. Thermostat failure in either open or closed positions causes problems ranging from poor fuel economy to engine overheating. System bleeding becomes necessary after any service that introduces air into cooling passages. Air pockets prevent proper coolant circulation and create localized hotspots that can damage head gaskets and warp cylinder heads. Proper bleeding procedures vary by vehicle design, with some requiring special tools or specific sequences to completely eliminate trapped air. Cooling fan operation deserves attention as part of comprehensive system maintenance. Electric fans should activate at predetermined temperatures, providing additional airflow when vehicle speed alone cannot provide adequate radiator cooling. Fan motors, relays, and temperature sensors all contribute to proper operation, with failure of any component potentially leading to overheating during low-speed operation. The heater core, often overlooked in cooling system discussions, plays an important role in overall thermal management. This miniature radiator inside your dashboard can develop leaks or become clogged with debris, reducing heating performance while potentially causing coolant loss. Sweet odors inside the vehicle or foggy windshields often indicate heater core problems requiring attention. Preventive maintenance schedules should account for driving conditions and vehicle age. Severe service conditions, including stop-and-go traffic, trailer towing, or extreme temperatures accelerate cooling system wear. Older vehicles require more frequent inspection as rubber components deteriorate and metal parts corrode over time. Adjusting maintenance intervals based on actual conditions prevents problems before they develop. Professional cooling system service involves more than simple coolant replacement. Proper flushing removes accumulated deposits. Pressure testing identifies weak components before they fail. And chemical testing reveals coolant condition between changes. These comprehensive services cost more than basic drain and fill procedures, but provide valuable prevention against expensive failures. Understanding temperature gauge readings helps identify developing problems before they become critical. Normal operating temperature varies by vehicle, but consistent changes from established patterns warrant investigation. Gradually rising average temperatures may indicate partially restricted radiators, failing thermostats, or degraded coolant requiring attention before complete failure occurs. Modern vehicles incorporate numerous sensors and control modules that affect cooling system operation. Coolant temperature sensors inform engine computers about thermal conditions, affecting fuel mixture, ignition timing, and fan operation. Sensor failures can cause poor performance, increased emissions, and potential engine damage if incorrect information leads to improper control decisions. The relationship between cooling system health and overall engine longevity cannot be overstated. Engines maintained at proper operating temperature experience less wear, consume less fuel, and produce fewer emissions than those suffering from cooling system neglect. The relatively modest investment in proper cooling system maintenance returns dividends through extended engine life and reduced repair costs. Environmental considerations increasingly influence cooling system service decisions. Proper coolant disposal prevents groundwater contamination, while extended life formulations reduce waste generation. Maintaining optimal cooling system efficiency reduces fuel consumption and emissions, contributing to environmental protection while saving money on fuel costs. Emergency preparedness should include basic cooling system knowledge and supplies. Carrying spare coolant, basic tools, and understanding temporary repair techniques can prevent minor problems from stranding you in remote locations. Knowledge of safe practices around hot cooling systems prevents injuries that could compound mechanical problems with medical emergencies. The evolution of cooling system technology continues with developments in electric water pumps, variable speed fans, and advanced coolant formulations. Understanding current technology while preparing for future developments helps make informed maintenance decisions that protect your investment while ensuring reliable operation, regardless of driving conditions or vehicle age. Your cooling system silently protects your engine every mile you drive, asking only for periodic attention to continue its vital work. The knowledge and effort invested in proper maintenance pay dividends through years of trouble-free operation, preventing the frustration and expense of cooling system failures. Taking proactive measures today ensures your engine remains protected tomorrow, regardless of external temperatures or driving demands placed upon it.